Hi everyone and welcome to this video. And now we want to talk about structures of hybrid models. We basically saw before that we use two different kinds of models within hybrid models, like first principles or mechanistic models, and on the other side data-driven models. And now you could imagine that there are different ways to combine them together. And one way would be to say, okay, I do it in a parallel manner and say I have a black box model and I have a white box model. I put them in parallel. So this is the white box. And I put them in parallel and use them together. So the black box model gets an input U1. The white box model gets an input U2. Both models have parameters, theta1, theta2, and there's a result coming from the model, which is then actually combined. So the result of the top one is, or the black box model is f from U1 and theta1, and down here we have g from U2 theta2, and the overall result would be y, the output. And I add a legend, so you are external independent and inputs theta are model parameters, and y are dependent outputs. And basically what you can use with this parallel hybrid model is, or when you can use it, is if you have a mechanistic model available, but this mechanistic model is not very accurate. So mechanistic model not very accurate. Then you could use like the data-driven model to correct the mechanistic model. So the output of the mechanistic model is not used as the actual output anymore, but you add a part on it and provide then your output. So data-driven model corrects output. So this is basically what you can do with the parallel structure. And then on the other hand side, you could also think of serial structures. One would look like the following. You have an input U2, which goes into a white box model. And then this white box model has again a parameter set. And from this white box model, also this function value comes. And this feeds again into a black box model. And also there is a feed from the outside with U1. The black box model has another parameter set, theta1. And then it calculates an output f from g from U2 and theta2, and from U1 and theta1, and the final output is then y. This is one option. The other option would be to say I change it and say I have a input u1 into a black box model with parameters theta1. From these values I calculate my function value f from u1 and theta1, and this goes into a white box model. In addition, you have an input u2 into the white box model, and the white box model calculates the function value g from f from u1 theta1 and from u2 and theta2, which is missing down here, and calculates again an output. Basically, this is called the serial hybrid model. And you might use it if you have parts in the system which are well understood, where you have an accurate white box model, and at the same time you have parts in the system which are not so well understood. So, and then you use like a white box model or mechanistic model for the parts which are well understood. So parts which are well understood. Mechanistic model or parametric, and then parts which are not well understood. Here you use a data-driven model, as non-parametric model. So one well known application in process systems modeling or also in bioprocess modeling is that you say this white box part are some kind of differential equations, some kinds of balance equations, and maybe I also have some parts regarding the kinetics and the transport terms which are white box, and then you have a growth kinetic or something which is hard to capture, and here you use a data-driven model to describe it and feed it into the white box. Overall, you could also think of combining these architectures. So you could say, okay, you have this white box model, which would be a balance equation, and then you have here you have a parallel architecture for the kinetics, like saying, okay, I have a basic clue of this kinetics and I correct it with the black box model. So this is also possible. Thanks for watching, and I see you in the next one.